And let's start with this. So first of all, what is a quadratic residue? A quadratic residue is just the square of a number modulus p. That's what it is. So you take a number from 0 to p, you square it, and you make it modulus p, and that's it. Move this out of the way. Okay. And then what is the idea of the talk? So we know that these quadratic residues are between 0 and p minus 1. They are integers. The idea is just to compute them, add them up, and see what happens. That's the idea of the talk. From 1 to p minus 1. You will say, why don't you start with 0? Because 0 adds nothing. So that's why we're going to start with 1 up to p minus 1. Okay, let's start with an example. Here we have 2 primes of the form 4n plus 1. One of them is 5, the other one is 13. On the left-hand side, I have all the quadratic residues. And on the right-hand side, the ones for p equals 13. Let's take a look at the left-hand side. Look at the table on the left. All right, so the residues are here. They add up to 10. And for instance, k equals 3, when you square it, that's 9. 9 is congruent to 4 modulus 5. K equals 4. When you square it, that's 16. But 16 is congruent to 1 modulus 5, right? Modulus p. And the sum is 10. The other sum is 78. I'm going to give you 30 seconds to see if you can come up with a formula. I'm going to give you 30 seconds. Try to think of a formula. It's an easy one. You can put it in the chat when you find it. So, okay, I found this problem online, and I say, hey, there's a beautiful formula when p is of the form 4n plus 1, and actually the formula exists. It's easy. And here's another example. When p equals 17, the sum of the quadratic residues is 136. I was wondering if your formula that you found works. If it works, you are very good. If you found the formula, that means you are very good. If you didn't find the formula, you are going to be very good, okay? You are in the way to be very good. Okay, so actually the formula is p times p minus 1 over 2. Simple. That's what math is most of the times, right? Beautiful, simple. I like it, right? It's nice. All right, let's change here the strategy a bit. Let's change the prime. This time is of the form 4n minus 1. Here we have 2 more examples. On the left, p equals 7. On the right, p equals 11. And here are 2 numbers, like the sum is 14 and the other case the sum is 44. This time I'm not going to give you 30 seconds. I'm going to give you only 20 seconds and see how you do. Thank you very much. I'm not going to give you the answer. I'm going to give you another case, actually. I want to take a look of the number p equals 73. Let me come back. Take a look of these charts. Look at the beautiful symmetry. Like all the numbers they appear twice in pairs. 1 and 1, 4 and 4, 2 and 2. Right here, 1 and 1, 4, 4, 9, 9, 5, 5, 3, 3. In other words, it's enough to compute the sum of residues up to half of them, and then you just multiply by 2. And they appear like in this chart, they appear like in a mirror, right? It's a beautiful symmetry. Let's take a look at this case, p equals 23. I only did half of the chart because I know that's enough. Then at the end, you multiply by 2, and that's it. So I have colored them in such a way for you to see the pattern that I observed when I tried this for the first time. I did it with 50 primes. You say, gosh, that's a lot. I know it's a lot, but let's take a look. 1 plus 6, that's 7, right? If you have the first and the last one, that's 7. Let's take a look of the yellow numbers. That will be 4 plus 8, that's 12. If you have 7, you want to have 12, you need 5 more, right? Okay. Now take a look at the white ones. 9 plus 12, that's 21, right? 21, you just add 9 to 12 and you get 21. That's the white ones. What about these blue ones? 18 plus 16, that's 34. 34, that'll be, if you add 13, that's 34. Oh my goodness. We're looking at a beautiful pattern. Look at this. 5, 9, 13. Oh, we are seeing a nice pattern here. What the heck is happening? Let's take a look. Now, let's take a look at the next one. The red numbers, 2 plus 3 is 5. And oh no, we were supposed to get 51, right? That's when I became sad. Say, oh my goodness, everyone can feel sad because when they are looking for something, they cannot find what they want. Everyone can feel, it's so easy to get sad and get depressed and stressed and like down, right? Say, hey, maybe not all of it is lost, because if you have 34 plus 17, that's you're supposed to get 51. But wait a second. What if we remove a multiple of 23? What if we remove 46? The answer is 5. Oh, and that's when I became happy again. Say, okay, maybe there is a pattern, but it's broken, but we know how to fix it. Then we can continue, all right? So here is what I found. I know it looks like a lot of formulas, but this is exactly what's happening. So when k is between some range, between two numbers, if you add the first and the last one in the table, you get something, but you have to subtract a multiple of the prime. Whereas if k is in this other range, this sum also gives you the same thing, but this time you subtract an odd multiple of p. And so this corollary, like this comes from some little lemmas. It looks simple, yes, it may be simple, but it's a pattern that nobody has found ever before. So it's worth of just observing it, right? And so let's see what happens. So I'm going to rename these numbers, these endpoints. I'm going to call this Q and this R for root, Q for, because I had a girlfriend whose name was Quantanella. No, I'm just kidding, all right? I'm just putting those names like that. All right, here we go. I'm renaming this. They're just different names. And it happens that when you add the sum of the residues, many things cancel out and you end up with this formula, right? Here, this is the floor of the number, the maximum integer less than or equal to this Rm or Qm, right? So you might think, wow, this formula is long and it seems difficult. You're right. The formula that we saw when P was of the form 4n plus 1, it wasn't like this. It was something simple, but this, we have to do something. Oh my goodness, this is hard, this is long, but it's something, all right? It's something. All right, let's take a look of something called the ring of integers. This talk is about the class number, and to be honest with you, I didn't know what the class number was until I found these quadratic residues. So let me start by defining what is the ring of integers. The ring of integers is this quadratic field, which is a vector space over the rationals, it has dimension 2. And each element of this field satisfies a polynomial. In other words, it's a root. And P of x is a monic polynomial with rational coefficients, right? So it happens that when the coefficients of the polynomial are not rational, but integers, it's called an integer, right? That's what we call the integers of this field. Now, the discriminant of k is the discriminant of the quadratic polynomial. Listen, if at some point you say, hey, I'm not understanding anything, I'm not getting anything, I don't get anything. So you may say, hey, I know quadratic formulas. I know how to compute the discriminant of a quadratic formulas. Start with that. Start little by little. Grab something that you really understand. And from there you can go, all right? So the discriminant is negative 4p. So this is the integers and they form a ring. So we denote this ring of integers with OP, right? That's the ring of integers. Again, integers are those whose monic polynomial has integer coefficients. All right, now let's go to what this talk is about. It is the group of ideal classes, right? The ideal classes group. So we define the fractionary ideals as subsets of the quadratic field that are closed under multiplication and addition, and there exists an element in the ring of integers such that when you multiply it by the set, you get a non-trivial ideal, right? It sounds like I know a lot about ideals, but I don't, right? That's not my specialty. But I just got into it a little bit. So the group of ideal classes is the quotient. And in algebra, each time you do a quotient, you get something beautiful because you observe things from a higher perspective. You say, hey, when you do these quotients, you identify things that are equivalent. You say, hey, so okay, this is the same object, so what? All right. So it gives you a nice perspective when you do these quotients. This quotient is the group of ideal classes, right? You divide the fractionary ideals by the ones that are principal, right? And that's the group of ideal classes. And precisely the class number of this quadratic field is the order of this group. All right, in this case, my field is going to be imaginary. In other words, you count the elements of this group, and that is the order of the group, the class number, okay? Well, let's put some interesting things about it. Gauss, the famous mathematician, he conjectured that there is only a finite amount of imaginary quadratic fields of class number 1. In fact, this happens when the number inside the square root has these values. This was demonstrated in 1966. Were you born by that, Juanita? Were you born by that one? I'm not sure, all right? I was already born by that. I had 1 year old. I was 1 year old. All right, the quadratic fields are very interesting in number theory. Why? They by themselves have beautiful structures and you can count them. It's about dealing with the discriminants. I mean, they are interesting on their own. Gauss also conjectured that there's an infinite number of real quadratic fields with class number 1, but this is still an open problem. The formulas to find the class number are indeed very complicated and they involve the Dedekind zeta function. In fact, I'm about to give you those formulas. So this is a theorem that I didn't prove it, like someone did, and the sum of the quadratic residues is this minus p times h, where h is the class number. And the class number can be given by this formula, or this formula, or this formula, or this formula. In formula number A, this parenthesis, round parenthesis symbol is the Legendre symbol. In here, this is called the Dirichlet class number formula. It's the most famous class number formula ever. And this symbol is the Dirichlet character. This one is the Kronecker symbol. And this is just another expression for the class number. Yes, they are all complicated, right? So let's go ahead and put all the things together, right? So on one hand, we know that the sum of the quadratic residues is given by the previous term. But on the other hand, we have this beautiful formula that we got from the observed. You remember the colors, the beautiful pattern? We got that formula. And let's set them equal to each other and we solve for h. And what we get after renaming gamma k, like this sum right here, we can solve for h, and it happens that h has this expression. Now, you tell me, do you think this formula is very complicated, like the one from Dedekind or Dirichlet? No, this is something that you can grasp because it's based on the floor of a number, right? So it's a beautiful formula, at least I see it that way. It's a nice formula. So when I send this paper to this magazine, usually the magazine say, oh my goodness, you have to rewrite the paper. We don't like it. Doesn't satisfy the requirements. Doesn't meet the standards. But this is the first time they have ever said to me, oh, congratulations. This is a beautiful formula. And I'm just happy that you guys are like looking at this formula because I felt a lot of excitement when I did it for the first time. Okay, so here's an example. P equals 103. The number is of the form 4 times n minus 1. I compute this floor of these numbers. Remember, these are the edges, the extreme values of those intervals. And it happens to be that gamma 6 equals 212, and the class number is 5. So counting the elements of counting these ideals, it's really complicated. But this formula allows us to, hey, boom, we get the number 5 super fast, right? And I have a second example, but I'm not sure if I have enough time to do it. And it's very similar to this one. I just would like to say, thank you for being here. Thank you for Catalina Camacho for being a great source of information. I bothered her a lot. Oh my goodness, I asked her a lot of questions, but she was very kind and to answer all of them. And thank you for my awesome audience for being here today. Thank you very much. So if you have questions, I am here to answer any questions.
Thank you, Jorge. And no, you didn't bother me at all. I hope I was helpful. I don't know do we have any questions? Because I think if we don't, then maybe we can, like you said, you had another example. Maybe we can.
Yeah, it's very quick. And I just decided to jump up a bit higher. Say, hey, look at this number. You might say, oh, this number is not prime, but yeah, it is prime number. I already checked it. Okay. And I computed this number using the software Maple 2019. And I got this. It took a while because it's a lot of computations, right? It's a lot of the floors of many numbers. But after I got it, I computed this and it was 523. And if you look at the formulas for the class number on the sources to compute it, it's a pain. It's a pain in the neck. It's very hard to compute it. But you know, it takes a bit, you know, long in the software to compute it a little bit. So, but it's much easier than the previous formula. So, thank you.
Thank you. Now, do you have any questions or comments? Christelle.
Yeah, thank you. I was surprised how big your gamma was for this example. Do they like get bigger and bigger? Do you have any idea how that behaves?
Indeed, yes, that gamma, it approaches to infinity, but there are other ways of computing it in such, I mean, I can arrange the terms in such a way that many cancellations happen, and maybe I can express it a slightly different way. So where the term is not that big. And by the way, when I was observing the sums, I saw some behavior of some quantities that was up and down, something oscillating. And I'm researching on that. I have 2 coming papers about it, and I call those jumps. Those jumps are very interesting.
Nice, thank you.